So page 21. If I don't assign them for homework, you can if you want extra practice, but it's not required. All right. Shh, shh, shh. Okay, so dilations. So what specifically is a dilation? A dilation is a transformation that moves each point of the original figure along a straight line drawn from a fixed point, which is called the center of dilation. Now, the description of a dilation must include the scale factor or ratio and the center of dilation. Now, what makes dilations different from every other transformation we've done? Well, dilations produce figures that are the same shape as the original, but not the same size. So, in other words, dilations are not a what? A rigid motion. So, it violates the rules of rigid motion. So, it's our first type of a non-rigid motion transformation. So essentially all a dilation does is it makes a shape bigger or smaller depending on what the scale factor is. All the angles are still congruent, but the sides are not. Yes. No. If I don't assign it to you guys, you don't have to worry about it. You can do it if you want extra practice, but again, if I don't assign it, I'm not grading it. So, now, let me ask you guys this. If rigid motions create congruent figures, what type of figures does dilations create? Well, non-congruent, but technically, what's the term for it? So same shape, different size. What's the term for that? Nope. Starts with an S, though. Close. So if something is not quite exact, what do you call it? Similar. So a dilation doesn't create congruent figures, but it does create similar figures. And all similar means is exactly what a dilation describes. It's the same shape, but a different size. And we'll talk more about those when we get into Unit 2. Now, scale factors. A scale factor, if it is greater than 1, the dilation is called an expansion. So if you don't know your vocabulary, that's just a fancy word for bigger. Now, if your scale factor is less than 1, and I don't really want to say less than 1, I would say it's more between 0 and 1. So if your scale factor, let's call it S, is between 0 and 1, so what type of number is that if it's between 0 and 1? It's a decimal or a fraction. So it's a true fraction. So in other words, if your dilation's a fraction, by fraction I mean a true to God fraction, not an improper fraction. What do I mean by that? Numerator is smaller than the denominator. Improper fraction, the numerator is bigger than the denominator. So technically, an improper fraction is greater than 1. A true born fraction means numerator smaller than denominator. It's, when you guys were in elementary school and you did the little factor blocks, like let's cut this in half, let's cut this in thirds. You know what I mean? So that is what we call a compression. And that's just a fancy word for it's getting smaller. Now, you will hear these words again when you get to function transformations, which will be a little bit longer down the road. So, some properties of dilations. Like I said, the image and pre-image are the same shape, but not the same size. So they're similar, but they're not congruent. The angles are moved to angles of the same measure. So that also corresponds with same shape. Same shape comes from all angles being congruent. The ratios of corresponding line segments given the scale factor, so you would either do it by new divided by old or image divided by pre-image. So in other words, that's just a fancy way of saying that they're proportional. So if you divide the new side length by the old side length, you'll get the scale factor, which is what you multiplied to get that side length. The area of that figure will increase by that scale factor squared. Why do you think it's the scale factor squared? Think about area. Why do you think it's scale factored squared? Why would it not? Well, kind of. What is area? That's a rectangle. But what is area? Golden, what you got? It's the amount of space within a shape. All right. It's the amount of space within a shape, a 2D shape. All right. So if we're talking area, typically we measure area in what type of units? Square units, depending whether it's feet, inches, centimeters, whatever. Square units. Why do you think it's square units and not just units? Units will be in the 1 dimension. Square units will be in the actual 2-dimension plane. So like, for example, if you look at this graph, see how they're all in squares? If we count those squares, number of squares, that's our area. So the reason that's the scale factor squared is that the scale factor itself would be a piece of the perimeter. We would have to square the scale factor to account for adding in all those little squares to make it bigger. Just a little piece of math trivia for you. So in other words, volume would be what? That's still volume of a rectangular prism. If you a cubit. So volume is typically written in units cubed because that's the number of cubes you can fit in a space. Area is the number of squares you can fit in a given space. Volume is the number of cubes you can fit in a given space. Difference between 2D and 3D. So get out of the habit of saying area is length times width and volume is length times width times height, because is that true for everything? No, it's not. If I asked you area of a circle, it is not length times width. If I asked you volume of a cylinder, it is not length times width times height. All right. So, you guys, so this is kind of the curse of being an honors kid, and I would know this because I was one. You learn all these formulas, but then you don't actually know what they're telling you. You just know, oh, I just need to plug it into this. But you don't actually know what it actually is describing. All right. And to be honest, I didn't learn a lot of this stuff until I got to college and professors forced me to understand what it was like. All right. So I'm teaching you guys this now because if you know what these words mean, it expands your mathematical knowledge, allows you to think a little bit more outside the box. All right. So yeah, even though it has nothing really necessarily to do with this topic, knowing that area is the given space inside a 2-dimensional plane, that'll help when you start doing things like in Math 3, when we start doing more complicated surface area and more complicated volumes, things like that. All right. Because trust me, because I teach Math 3, there are some things in Math 3, you will see volume and surface area again. And if you don't know exactly what it means in a general sense, it'll be kind of tough. All right. So, moving on. Dilation, which does not pass through its center of dilation, will travel parallel to the original image. So, in other words, let's say that your center was the origin, but none of the points was on the origin. All right. That means it'll run parallel to itself. So, for example, here's one example where it will run parallel to itself. So AC is parallel to A prime C prime. BC is parallel to B prime C prime. AB is parallel to A prime B prime. Whereas if you look at this shape, the center was the origin. So since they had a point that was on the origin, it did not run parallel. It actually kind of, part of it still contained within the original shape. All right, and that's the next point. So a dilation which does pass through the center of dilation travels on the same line. So that's why if you look here, part of this side is still on the original. It's on the same line. Now, to actually calculate a dilation, it's really easy, especially if it's centered at the origin. So this is kind of the standard that you'll see a lot in this class. If it's centered at the origin, the way that you find the dilation is just multiply the coordinates of the vertices by the scale factor to find the new coordinates of the dilated figure. So if we wrote that in arrow notation, if we start with xy, you're given kx times kx ky, where k is your scale factor. So just to put it in more layman's terms, let's pretend that k was equal to 2. So your scale factor was 2. So what you would do is for every point that you have originally, you would multiply the x and y values of those points by 2. Another way to write dilations is in function form. So that would be capital D, and then the subscript would be your scale factor, or k. So for example, going off of if k was equal to 2, that would look like capital D with a subscript of 2. So it's saying you're doing a dilation by a scale factor of 2, or a dilation by a scale factor of k. Now, the function notation, so like the letter notation, so like when we learned capital R, 90 degrees is rotation counterclockwise by 90 degrees, and little r, y equals x is reflection over y equals x, and big T, 1, 3, that means right 1, up 3, translation. We don't really see them much when they ask us to dilate or translate, but you will see them again with compositions, which we're learning tomorrow. So let's just do some simple ones. So they gave us these original points, and they gave us the rule, if xy, then the dilation will be 2x, 2y. So what's my scale factor? 2. So my scale factor is equal to 2. So what am I essentially doing to all of these points? Multiplying each part of them by 2. So what would A prime be? 6, 8. 3 times 2 is 6. 4 times 2 is 8. What about B prime? 8, negative 4. C prime? Negative 4, negative 2. And then if I graph it, I have 6, 8. That's A prime. 8, negative 4 is B prime. And negative 4, negative 2 is C prime. So my picture will look something like this. Now, do you see how each corresponding side is running parallel to each other? So, for example, AC and A prime, C prime, those segments, they're running parallel to each other, so they have the same slope. All right, that is a factor of dilations if the point is not going through the actual center. And the center of dilation is the origin, so right here. So it doesn't go through it, so that means all the sides are parallel. All right. Now, I'm not so worried about the graphs of these. I'm more so worried about can you get the points. So, for example, 2, I'm dilating that parallelogram STUV by a scale factor of 1/2. So if I'm multiplying everything by 1/2, what am I actually doing? Dividing it by 2. So what would S prime be? 4, 5. What would T prime be? 3, 3. U prime? 6, 3. And V prime? 7, 5. Now, just for funsies, if I wrote that as an arrow notation, what would it look like? 1/2 X, 1/2 Y. That's how you would write an arrow notation. All right, what about the next one? So we're going by a scale factor of 2. So what am I multiplying by? 2. So A prime would be 610. B prime would be 6, 6. C prime would be 10, 6. So as an arrow notation, what would that look like? 2x, 2y. Now, that is if you are rotating around the origin. But this is honors. So let's look at when we're not rotating around the origin or when we don't know the scale factor. So this is the fundamental theorem of dilations. We kind of already mentioned this, but if line segment AB is dilated using center point C, not necessarily origin, just a center point, and it's not on AB, the scale factor of K, that means that if we do the segment A prime B prime would be equal to K times AB. So the length of A prime B prime would be K times AB. And those two segments would be parallel. So if we look at our figure here, C is clearly our center point. So C is our center. AB and A prime B prime are parallel to each other. That's what those little arrows mean, meaning they will never intersect. So let's say that A was X in length. So if the scale factor was K, what would the length of A prime B prime be? If the scale factor was K, KX. Now, the next exercise kind of puts that into practice. So the image below is MN, and MN is the image of KL with a dilation centered at point C. So MN is an image of KL. So which one came first? KL came first. Because remember, image means it's after translation. Pre-image means before transformation. So KL is my pre-image. Now, first off, how do we find point C on this graph or on this table? How do you think I would find point C? It's not going to be in an exact spot. It'll be pretty close, but it is exact.
Trying to find the area?
Not necessarily. Say that one more time. Right. So we use the lines of MK and NL. All right. Kind of like this picture right here. Do you see how there's like a little trapezoid right here? Well, they just made it into a triangle by connecting those lines because they do intersect. And where they intersect is point C. So if I continued those lines, wherever they intersect, that's point C. Now, how would I find the scale factor? How do you find scale factor if you know what the two sides are? Divide the sides, but which one comes first? It's new divided by old, or image divided by pre-image. So what's my new side length? 12. What's my old? 16. Now we know that's not going to be a pretty number, so we just got to simplify that fraction, which just simplifies down to what? 3/4. So that's equal to K. So that's your scale factor. Now, let's check ourselves really quickly to make sure we have the correct scale factor. So if you have it down in your mind, check it. So I'm going to do 16 over 1 times 3 over 4. How do I multiply fractions? Straight across. 16 times 3 is 48. 1 times 4 is 4. What's 48 divided by 4? 12. So we get our new. So we have the correct scale factor. Yes, ma'am. You could. Yeah, you could. Now, explain why MNLK must be a trapezoid. So what's true about trapezoids? What do you know about trapezoids? They only have one set of parallel lines. And what does it say about if we're multiplying a side by a scale factor? The sides must be parallel if they're around the same center point. So this is a trapezoid because it has one set of parallel lines, or parallel sides, I should say. That's a defining feature of a trapezoid. Now, we've done around the origin, so now let's look at, so skip page 23, go to page 24. Yeah. Let's look at some centers that are not the origin. So some centers that are not the origin. All right. So our center is 9, negative 12, and we're going by a scale factor of 4. All right. So the center is at the point 9, negative 12. So that's right here. So this is where it gets a little bit different. All right. Because we know that the side lengths will have to be expanded by a scale factor of 4. However, we don't know for sure where those new points will land because we know it's not going to go through the point 9, negative 12. So because it won't go through that center, what's true about the sides of our old, which is currently graphed, versus whatever we graph next? What's true about those sides? They have to be what? They have to be parallel. So, in other words, it's just a matter of doubling or quadrupling your rise over run. So, for example, to get from D to H, all right, I would go up 2 over 2. All right. Now, that's to get from D to H. But let's say I'm just trying to get to H from my center. So similar to how we found slope from all the points on rotations. If I go from my center, I only have to go up 2 to get to h. So the slope for h, so the slope of h is equal to, my rise is 2, my run is 0. So if I'm going by a scale factor of 4, how do you think I'm going to find my new point? Multiply your slope by 4. Now, don't pay any mind to the zeros. I'm just writing in terms of rise over run. So 2 times 4 is 8. 0 times 4 is 0. So I would just go up 8. So 2, 3, 4, 5, 6, 7, 8. So this point right here would be my new h. So h prime. And I'm going to do the same thing to the rest of them. My slope of d. I don't go up or down anything, but what do I go to the other side? I go left 2. So I'll write that as a negative 2. Times it by 4. So I go up nothing and to the left 8. So I count 8. So 1, 2, 3, 4, 5, 6, 7, 8. Yes, sir.
So are you just like counting how many dots the point is away from the center dot and then multiplying that by the constant?
It's mainly just slope.
The slope would be 2. That's 1. 2 up and 2 across is the slope of 1.
Yes, but what I'm saying is it's not so much slope, it's more so the rise over run. So you're multiplying the rise over run by 4. So like it's the unsimplified slope. That's how I would put it. So unsimplified slope. Because obviously this would be undefined, this would be 0. But if we're talking about, because we're just trying to figure out what the new rise over run will be. So I would say it's the unsimplified slope, if that makes more sense. So for g, we still go out 2, but it's to the right instead. So it'd be 0 over positive 2. So if I times it by 4, it'll be 0 over what? 8. So that means I'll go up none over 2, 4, 6, 8. Now, E and F, we'd actually have to do some more stuff to it. So up, yes.
Why would you just put why would you just count the block given that each number, like each block says 3 apart? Like when you look at the graph.
Oh, yeah. Yeah, I know what you're talking about. Yeah, I didn't notice the scale. That's my bad. So in reality, this is, but it would end up in the same spots though, because for example, this is that's 6. So 6 times 3 would be 18. Or no, 6 times 4 would be 24. So 6, 12, 18, 24. We still end up on the same dot wise. So what he's saying is that if you look at the actual scale, it's in terms of 3. So if we go 2 up, that's the same thing as 6. So that'll just be 24 instead of 8. Same thing here. Instead of negative 2, it'd be negative 6. So that'd be negative 24. And so this one would be 6. So that'd be positive 24. But if you think about it, if you simplify the fractions down, like just taking out scale factors, it would still be 2. It would still be all the way down. All right. If we divided all of them by 3, it'd still be the same distance. All right. So for E and F, this is where you actually have to pay attention to the slope. So if I go down, and remember each one is 3. So if I go down 2, that's technically down how many? It's down 6. So let's call that negative 6. And then over 1, so that's over what? So it's in terms of 3. So over 1 is actually over 3. I'm going to multiply the top and the bottom by 4. That's technically what I've been doing the whole time, but just, anything times 0 is 0. So my new rise or run is down 24 over 12. So if you want that in terms of like the blocks, so you're not confusing yourself, that's the same thing. If you divide it by 3 over 3, that's the same thing as down 8 over 4. So my new point is if I count 8 blocks, so that's in sets of 3, so that's technically 24. So 1, 2, 3, 4, 5, 6, 7, 8. And then go over 4, which is the same thing as going over 12 because it's in a scale of 3. So 1, 2, 3, 4. There's my new E prime. And F would be the exact same thing, except instead of going to the left 3, you're going to the right 3. So you're still going down 6 over 3 times it by 4. Times it by 4 over 4. So that'd be negative 24 over positive 12. So again, if I divide it by 3 over 3, that would tell us how many actual squares that is on this table. So negative 8 over 4. So I would go down to 8 and then over 1, 2, 3, 4. So my new figure will look like this. Crap. Now, I know that was kind of confusing, so let's do another one. So let's look at number 2. So the center is 2, 1. So 2, 1 is right here. Nope, that's not 2, 1. This is 2, 1. All right. Now, it's kind of hard to see, but these are the original plots. So that's V, S, W, T, and U. Now, we're going by a scale factor of 1/2, so we're technically doing what? Dividing it by 2. All right. So it's pretty much the same process. All right. The only difference is that since the center is on our shape, then our shape is going to fall on the same line as the others. All right. It'll be pretty much on the same line. So how far away is our center point from S slope wise? It's just to the right 2. So not to the right, good God, to the left 2. So if I half that, what am I actually going for my new point? The left 1. So this will be S prime. For W, what is it? So if I go up how many? 2. So if I half that, what is it actually? Up 1. So that'll be W prime. What about for T? How far away is T from the center? 4. So if I half it, it'd be 2. So that's T prime. Now, think carefully. What's the rise over run to get from the center to V? How go up how many? 4, and then over how many? 2. So if I half both of those, how much am I going up and over? Up 2 over 1. So there's V prime. And then lastly, D. How far away rise over run wise is D, or no, that's a U, is U from the center? It'll be 4, 4. So this would be what? 2, 2. So up 2 over 2. So that's W prime, U prime. So my new shape looks like this. So it's still connected to the shape, but it still got smaller. Does everyone kind of understand how you would go about this? Okay. So your homework for tonight is page 23 and finish the rest of page 24. So do number 3 on your own. So you guys got a solid 40 minutes until class. Actually, no, it's more like 30 minutes until class ends. So don't forget the Delta math from yesterday is due tonight by midnight. So if you didn't finish it yesterday, you can work on that. The paper homework that I just assigned, I will check first thing during class tomorrow. If you finish everything, work on your journal. All right, so go ahead and get to work. Yes. Oh, well, actually, I said put your name on the board. Then, yeah.